So we have Dr. Prabir Barooah here, and he is an assistant professor in Department of Mechanical Aerospace Engineer at University of Florida. He received his PhD degree from University of Santa Barbara, California, Santa Barbara. He was a research engineer at United Technology Research Center. His current research is focused on estimation and control of interconnected systems, such as mobile sensor networks and energy systems for smart buildings. So please join me in welcoming Dr. Barooah.
Thank you. I took the liberty of changing the name of the symposium slightly, because my talk is going to be heavy on the physics side, so I thought I'll call it Symposium on Physical Cyber Systems instead of Cyber Physical Systems. So I'll be talking about smart buildings. I think the title of the talk, as given in the schedule, says something about smart buildings, but really smart buildings is a very broad phrase. And in fact, what I'm going to talk about, what I work on, is energy efficient buildings. So I'm going to change the title slightly on building energy efficiency and estimation, and mostly on modeling and control issues. Before I get started on the details, I'd like to acknowledge all the people who have contributed to it. These are my collaborators from university and academia, from academia and industry. Martin is already here. And of course, all the students, both from Illinois and Florida and Columbia, who have done all the work that I'm going to present. And other collaborators who have helped in the project. And of course, financial support from National Science Foundation, without which none of this would be, I would not be here talking about this stuff today. So buildings and energy. Buildings consume a lot of energy. Actually, there are three main consumers of energy in the US economy: transportation, industry, and buildings come first in terms of energy consumption. Numbers are pretty large. Buildings are responsible for 71% of electricity consumption. And they are responsible for close to 1/3, a little bit more, of CO2 emissions. And within buildings, there are many consumers of energy within buildings. The primary ones are heating, ventilation, air conditioning, and lighting. So I'll be focusing mostly on, if we want to improve energy efficiency of buildings, we'll have to focus on those things, because you always look at where is the biggest bang for the buck. So I'll be talking about space, heating, cooling, and things like that: heating, ventilation, air conditioning. Lighting is also another part, but we have not done too much work on that aspect. If you look at some of the projections, this is from a LBNL report that's looking at projected energy consumption in the US by year, I forgot which year it was, 2050, I think. This shows the orange curve is business as usual. So if we continue operating buildings the way we do now, and with projected savings, this can be considerably lower. In fact, they predict about 55% improvement in the energy consumption of the buildings. So that big part of that projected improvement will come from improvements in control, particularly of heating, ventilation, and air conditioning. So there is room for savings. Otherwise, there's no point doing this, right? If the buildings are already operating close to their thermodynamic efficiency, there's no point doing anything, because that's what it is. But people who have looked at this issue, they recognize that there's a lot of improvement. There's a lot of opportunity for improvement. I am going to, of course, focus on controls. And the other reason for focusing on control, there are two parts. One is design, the other is control or operation. Design of buildings, of course, has a huge impact on energy efficiency. But design by itself is also not enough, because recently, because green designing is becoming a big thing now. And people who have tried this, it leads to strange results sometimes. So some of the so-called high-performance buildings, when they were designed and then they were operated, in some cases there's a huge gap between what was predicted based on the design and what is actually achieved. And part of the problem comes from not being able to improve the operation of it. So because I'm going to focus on heating, ventilation, air conditioning, I have to, for those of you who already know, of course this part is going to be boring. If you're not quite familiar with the physics of it, this might be useful. I'm going to give you a brief introduction of how things are done in commercial buildings. So commercial buildings, I'm going to focus on commercial buildings for two. I mean, residential buildings are a big part too, which the energy use is usually split half and half. One reason for focusing on commercial buildings is that any high-tech solution that we come up with, commercial buildings can actually absorb such solution. Residential buildings cannot right now because the economics is not there. So you have to come up with really simple solutions for that. And nobody's going to give me a grant for writing a paper for a simple solution. So I have to come up with more fancy stuff. That's why I focus on commercial buildings. So buildings have these things called air handling units, like big air conditioners basically. They are installed either on the roof of the building or in some floor between the top floor and the roof, which building operators fondly call the penthouse. So what happens is that there's the outside air that comes in, and some of the return air, some of the air that is exhausted out of the building is not completely let go. It's recirculated. That is to improve energy efficiency actually, because there's a lot of energy that is consumed in conditioning the air. You don't want to lose all of that. So all that is brought back into these air handling units. There might be more than one. In the air handling unit, you basically cool down the air quite a bit, so that some of the humidity in the air, some of the water vapor in the air condenses out, and that's how you get dry air. And then cold and dry air is supplied to the rooms, to the zones. In the zones, what happens is that there is a thermostat. Usually that's how things are operated right now. I'm trying to locate the air vents here in this room. Cannot really. That's a thermostat, but I guess the air is being supplied through those and also exhausted out. So what happens is a local controller. There's a one temperature sensor. In that case, it's over there, and that's supposed to be representative of the whole temperature in this room. And then there's a local controller that looks at the temperature, and then there's a desired set point of temperature. And it compares the two, and based on that, it does two things. There are only two inputs, two actions it can take, or two inputs it can change. One is the flow rate of air coming into the room. Other is the temperature. Although the air is supplied at certain temperature to the room, which is usually pretty cold because you cool it down really drastically, which is usually around 55 degrees Fahrenheit, but that varies from climate zone to climate zone. And at the supply point, the controller can actually reheat the air because if it determines that if I supply cold air at 55 degrees Fahrenheit, the temperature is going to go down too much, then it can reheat the air. So there are two things it can do at that point. It can, that particular controller at every zone, it's completely decoupled, so every zone is controlled independently, and that controller controls the flow rate through something called a damper. I don't know why it's called a damper, but that's the industry name for it. It controls the flow rate, and then there's another reheat coil which can either reheat the air or not reheat it basically, right? And all that air is flown back and all that. So there are several sources of inefficiency in this whole process, but the two main ones are design and operation. So these things are actually designed quite poorly. What do I mean by that? It's designed to operate optimally under conditions that the building is never going to see. All right, so it's designed for peak loads. By load, it means how much heat is going to be generated inside the room under conditions when outside temperature is highest, maximum amount of number of occupants in the room, etc., etc. So they look at this peak load conditions and design it so that when those conditions are there, the system can deliver the required performance. But of course, most of the time, rooms are never under those peak load conditions. And because of the design for peak load conditions, all equipment is over-designed. They don't have to be as big as they are. And other part is, of course, right now the way buildings are designed, they are closed boxes almost. So none of the natural lighting and ventilation that can potentially be used is not used. If you look at this building, for example, but this is changing because green design is becoming big. And if you look at most of the if you look at the magazine of high performance buildings, most of the new buildings, people are trying to improve upon these areas. You will see a lot of natural ventilation, which means like you don't use huge fans to push the air through. You let the natural thermal effects to take the air in and out. And of course, natural lighting is also becoming popular. But even if after you do all this, the other part is poor operation, and that has to do with this, what I call the open loop control. It's not really open loop control of zone temperatures. After all, there is feedback in the sense that it measures temperature and does something based on that. But it's still open loop in a sense that the building, after all, exists for its occupants, right? But all of this, in all of this control, the occupants really play no role. So it doesn't even pay attention to how many occupants are there and things like that. And there, of course, are equipment faults that it doesn't really pay much attention to, as long as there are no comfort complaints. And poor software interfaces, I guess I'll come to that towards the end. Right now, it won't make a whole lot of sense. So what I mean by this open loop control, and what happens because of this. So here are some data from one building in the University of Florida campus. This is a LEED certified building. So LEED stands for Leadership in Energy and Environmental Design. These are supposed to be really efficient, well-designed buildings. Okay, so I have to first tell you how the details of some of this control algorithm. So this is called a single maximum control. This is how most modern buildings are operated right now with local controllers. So what it does is that, as I said earlier, there are two things you can control, right? Either the flow rate and the supply air temperature. So what it does is that it looks at the temperature, and if the room temperature is between a high value and the low value, which is a cooling set point, heating set point, that's supposed to be comfortable range, more or less, okay? It supplies the minimum allowable amount of air, and that the minimum allowable amount of air is dictated by standards, mostly by ASHRAE standards. ASHRAE stands for American Society for Heating, Air Conditioning and Refrigeration Engineers. So they'll tell you what you can or cannot do in a building. So it supplies the minimum amount of air as long as the temperature is between these high and low points. If the temperature starts increasing, then what it does, it increases the flow rate of air, because nominal air supplied is at low temperature, 55 degree Fahrenheit usually. That varies though. And it goes on increasing until it reaches the maximum that it can, right? Because every piece of equipment has some saturation level. And after that, it just keeps supplying at maximum. It cannot do much more. On the other hand, if it goes the other way, if it starts becoming really cold, then it reduces the flow rate only up to the minimum, and after that, it starts reheating the air and goes and reheats it as much as it is capable of reheating, right? So ideally, this is what it should be doing, and maintain temperature. So there are building schedules. Building operators program this whole building control system to maintain these temperatures at certain times, and other times let the temperature float, because they say, well, building is likely to be occupied from 6 a.m. till say 8 p.m. or 10 p.m. and I want to maintain temperature during that time, and other times I don't really care. And of course, I'm going to say temperature all the time, temperature control, but really one of the key variables here is not temperature. It's indoor air quality. So the reason it's not allowed to drop down the airflow below a certain minimum level is because if it does that, then even though temperature might be in comfortable range, you will not get any fresh air, and that's going to lead to poor indoor air quality. That's actually much more significant variable, a much more important variable to control than just temperature. Because if temperature is not right, you will be uncomfortable. That's about it. If indoor air quality is poor, then you'll get sick, and over time, building operator will get slapped with lawsuits. So you don't want that. So if you look at this one data, one plot from one room for one day, it already tells you what are the weird things that happen in buildings that you can, if you can improve upon that, you can save a lot of energy. So the blue curve is the room temperature in that particular room. That's like 249 over there in second floor for 0 to 24 hours. And it's mostly at 72 degree Fahrenheit for 24 hours a day, although most of the time nobody is going to be there in that room at all, right? So it's maintaining temperature and airflow and ventilation levels throughout the day, which is bad. The other thing is the red curve is the supply air temperature. So supply air comes in at around 55 degree Fahrenheit, but most of the time it's actually higher. So what it is doing is that the controller is reheating the air to maintain temperature. Even when at 2 a.m. midnight, nobody's there, it's reheating the air because otherwise you won't be able to maintain 72 degree Fahrenheit, right? So if you have to get one conclusion out of this is that this control system as it is operated now, it is serving the space, not the people, not the occupants, right? And we don't need to serve the space. Space exists for the occupants. And the other problem is that there's a significant amount of reheating which is tied down to the way things are operated. There's a significant amount of reheating, and this is, I think, for a summer day in Florida. Okay, you don't need to reheat anything, but you have to because you're the way you are doing things. And this is one of the things that commercial buildings, this is one of the ways in which commercial buildings differ from residential buildings. You might occasionally get these letters from your utility. I get it all the time. Well, the way to save energy is crank up your thermostat just by 2 degrees in the summer. Well, here, if you crank up your thermostat, if you increase the set point by 2 degrees in the summer, guess what's going to happen? It's going to do more reheating. So you'll actually waste more energy because the air is supplied at 55 degrees Fahrenheit, right? So simple rules of thumb control that work for residential buildings do not work for commercial buildings because of the way things are operated, right? So there's further justification for actually doing something complicated. All right, so we talked about reasons for inefficiency. So the question is, well, what can you do to improve upon these inefficiencies? How can you make it more efficient? Well, by now you probably have understood what needs to be done. You control as it is needed. Right? Don't try to control the room temperature and ventilation levels when there is no need. So you can, of course, being a controls person, this is how I think about it. You may think about it in a different way. Somebody poses this problem to me, I'll say, well, let's apply optimal control. Right? Let's predict how things are going to happen based on, let's say I have models for weather, models for how occupants are going to change, how occupancy levels, meaning number of people in a zone or in a building is going to change. I'll construct some models for the thermal dynamics, etc., etc. I'll feed all this into a big optimizer, which will determine what I should be doing from now till the next half an hour, or now till next 24 hours, or now till eternity, if you can do that. So that it will minimize energy use subject to these constraints, which is temperature should be within some bounds, indoor air quality has to be maintained, the humidity has to be maintained, etc., etc. Now, to do all that, of course, we need models. We need sensors too. We have to measure stuff because, after all, there has to be some feedback, and there have to be some, these algorithms for optimization. And there's a final one, which is software. Now, software does not mean just software to implement this. There are other uses of software here. I'll get to that towards the end. So let's look at these components, right? You need all these models, and then you have to do something with this. So that's a big problem. First of all, constructing these models, buildings, the physics of what happens inside a building is very complicated. If you just want to solve for the flow field inside this room, that's a very difficult problem itself. People can do CFD, computational fluid dynamics, or some people call it colorful fluid dynamics, depending on your point of view. But that's a very difficult problem, right? Because it depends. It's very sensitive to the boundary conditions you set. Even to solve the CFD for this room itself is difficult. If you want to do it for a whole building, depending on how things are going to change, it's impossible. Very large, complicated models. So that has to be the complex physical phenomena. And there's time variation and uncertainty. Buildings change over time because the mechanical wear and tear, cracks develop over time, and the uses of the building changes, right? One time, 1 year, you might have these cubicles in one area of the building. And later somebody says, no, I'm going to put offices here, cubicles over there. I mean, UTRC, that used to happen quite a bit. I don't know if it still happens. So things change over time. And the last problem is, which is something I listed at top, large heterogeneity in design. So this is the problem I faced when I first started working on this area, is that there are so many design variations in buildings, it's just unbelievable. I mean, what I'm talking about, I showed you some slides about how things are done. This is just one possible design combination, right? You can have, I said something about VAV, I didn't explain what that is. That stands for variable air volume. So the airflow through the building varies over time because of the way control is done. The older buildings used to have constant air volume. Then some of the newer ones have something called dedicated outside air system. So this outside air and internal air is actually not mixed together, but they're supplied separately, independently, which is actually good for maintaining ventilation and temperature separately. And then there are all sorts of course, they can do natural ventilation. And you can do also, and that's only one axis. There are like 50 different axes, right? People have talked about ground geothermal pumps, groundwater hot ground loops, air side economizers, water side economizers. I don't even know most of what those things mean. I mean, there's an unbelievable amount of variations possible in design, which all make sense depending on the climate zone you are in. And of course, designers take into account all these things to come up with the best design for that particular area. So now if you want to do modeling and control, the question is, what are you going to model? Which system are you going to look at? So here is one picture I stole from the latest issue in high performance building. This is a building in Canada. I think the headquarters for Manitoba Power, hydroelectric power. I don't remember exactly what it was. So this was designed. This is not this is a design drawing, but the building has been in operation for some time. So this huge building is completely naturally ventilated. No big fans. So it's a cold air is sucked in, and they design it such a way that warm air goes out through the stacks. They call it use stack effects and things like that. And in terms of getting fresh air in, you of course get some fresh air in, but to maintain good natural ventilation, good indoor air quality, they have 3 huge gardens inside the building that supposed to produce enough oxygen for the occupants throughout the year. So this is just one variation, right? And of course, compared to that, you have the traditional building where a whole bunch of air handling units, chiller plants, etc., and the whole building is just a closed box, and you just force air through it. So you have to kind of focus on one thing, right? So we decided to focus on just existing buildings, not look at this very high performance novel designs. And the reason is that existing buildings, this is from a report in 2003, which is kind of old, but in 2003 there were 4.9 million existing buildings, and the new projects were only 57,000. So and the buildings last for about 40 years or so. That's the designed time span. So the existing buildings will have a much more effect. They do have a much more effect on the total energy used than newer high performance buildings. So if we can make an effect on existing buildings, that probably is going to be more useful. So that's why we focused on variable air volume systems, existing buildings. At least now we know what is the thing, what are the processes we need to model. So then there are controls in the building level air handling unit, but there are also controls at the zone level, and we focus on the modeling and control issues for the zone level because the ventilation demand flows upstream. What do I mean by that? So the amount of fresh air, if you're using a system like this, the amount of fresh air you have to supply to a particular zone will depend on the worst case scenario inside a zone. So if you have, let's say, this whole building is suppose the whole building is empty, only this room is full, but this room is completely full, and then you can say, well, the building is operating at 5% of its peak design conditions, so I should be able to use a lot of return air, only a very little outside air. But that is not possible because it's already mixed at the upstream part. When it comes to this room, the ratio of fresh air to return air is very low, and that is not going to supply enough fresh air that we need in this room. So you really have to focus at what happens in the zone level to be able to do something for the building. So look at zone level. For zone level control, so there are 2 things you can do, right? Supply flow rate, you can change that, and supply temperature. And outputs you have to control temperature, humidity, indoor air quality. So conventionally, the way things are done, there's a PID logic, or the PID loops, and there are logic, and there tries to just maintain temperature throughout the time. Now, if that's what you do, then there's nothing much you can do really. If you have to maintain temperature throughout the 24 hours, then I mean, where is the room for energy efficiency? Because some amount of heat is being generated, and that amount of heat has to be taken out. Basic thermodynamics. No amount of fancy control is going to change anything. But you really don't need to supply or don't need to maintain that temperature throughout the time. So what we propose to do is let it float when it is unoccupied. So, and when it is occupied, let it again float, but in a very small range. So in the unoccupied times, ideally you should be able to make it float wherever, right? Let it go where, I don't care what the temperature is, but that's kind of risky. And the reason is that when suddenly the room becomes occupied, if the temperature is far off from a comfortable range, it will take a long time for the temperature to be brought back, which is also the reason things people do in smart lighting, for example, are not really applicable. And the reason is that this whole physical phenomena that governs all this has slow time scale. It takes about 15-20 minutes after you turn on the vents, for example, for the temperature to come up. On smart lighting, you come in, lights up. You leave, lights turn off. And they call it smart lighting. In my opinion, it's not really that smart because after a while you have to kind of wave your hands around for the lights to turn off. So in my opinion, it's actually dumb lighting, but people call it smart lighting. Anyway, you cannot do that here because if you do that, by the time you come in, it's uncomfortable, and then you say you are waiting there for about 15 minutes or so. Okay, things start becoming comfortable. But then if you leave again after 15 minutes to get a cup of coffee, and this system is doing control based on just what is happening right now, it'll turn the system off again. It'll turn the airflow off. And then it'll become slowly tend towards the uncomfortable range. So depending on your time scale of movement in and out of the room and the time scale of the physical process, it might so happen, if you do control like that, it might so happen that the room is going to be comfortable only when you are outside, and it's uncomfortable all the time you are in. So you cannot really do control based on just what happens now. So you need prediction. So that's what this prediction of occupancy, temperature, and the environment which affects it too. So we need occupancy prediction, and that's a very hard problem, right? I mean, how do you actually do occupancy prediction? So we look at the easy problem first, which is temperature prediction, which is actually not that difficult. I mean, there are problems there too, but there are some RC network models that we can construct, resistors and capacitors. So the idea is every wall has some resistance to heat flow, and there's some capacitors which can absorb and maintain heat. So you can link up all these models together. You can come up with some sort of RC network model. And there are some nonlinear elements because you have to take into account the effect of moisture in the temperature, humidity. So I'm not going to go into details of this. It's not that exciting. But there are, at the end of it, you get some sort of bilinear model. And you can come up with, you can do prediction reasonably well as long as you pick these R and C parameters properly. And that's a problem. But we'll talk about that in a moment. Let me go into that. So the model calibration. Ideally, you should be able to get this RNC values from software because it's all should depend only on the material and the construction type. But it does not because that wall is supposed to have certain RNC value. But if there's a little gap between the door, even if the door is closed, that completely changes the resistance to heat flow. So they're highly sensitive to these small variations. So the numbers you get from, say, ASTRAE fundamentals or the software that people have written to do these things, they don't quite work, so you have to do a calibration, a little bit of calibration. And now the question is, how do you do this calibration? Because every wall has 3 R and 2 C parameters, so 5 parameters for every wall. And so 4 walls, you got 20 parameters, and you have only one output to match. So it's a highly over-parameterized problem. Almost any R and C value you can pick will be able to match the data. And the question is, how much accuracy do you need? What are the right R and C values, if there is such a thing as right R and C values? So we can do some prediction, some calibration, and this is all done by manual tweaking. So this requires some research about how to do this calibration and what is the right measure of error. Because if I just want to look at temperature prediction, I can do, there are a lot of non-unique sets of parameters that can predict the same output. So in terms of issues in modeling, that's one of the big issues. How do you actually find these RC values? Then comes the part which is actually more exciting, which is this occupancy prediction. Now, the problem here is that forget about prediction, just measuring occupancy itself is very hard. Right? So there are all sorts of sensors. People will try to sell you sensors that supposedly measure occupancy. They don't. All right? And most of these sensors, okay, there are some sensors that people use to do something called demand control ventilation. So look at, for example, CO2 sensors. Measure a CO2 level and supply flow of air based on that. It works for big auditoriums, movie theaters, does not work for small rooms. I'll talk about that in a moment, but one of the problems with these things is that they drift out of calibration very frequently. They're highly sensitive. And there are video cameras you can use and do some automated algorithms to process video frames to figure out the occupancy. But that's a research problem yet. You don't get very good reliable solutions. The other sensors people use, they are actually all, they're not occupancy sensors, they're what I call flow rate sensors that only sense whether something has changed in the environment. For example, these PIR sensors or optical tripwires, they trip whenever somebody crosses a light beam, for example. And the problem with these sensors, because they measure delta change, to get occupancy at a particular time, you have to add all these delta changes. And if every delta change is just a simple random variable with some constant variance, then at time k, the variance of your occupancy estimate grows linearly with k. And this is a well-known, people who know basic probability have no problem believing this, but whenever I talk to various stakeholders in the problem about this, and they don't seem to believe me, so we actually collected some data. So we installed these sensors in this building. The building has only two entrances. So we installed 2 sensors. These are very expensive sensors. I mean, those previous ones that are listed, they're not supposed to be very accurate. So we bought these super expensive sensors. Each of them cost $2,000. They're supposed to be really high accuracy. And at the end of the day, these sensors predict that the building has 50 people at 12 midnight. And at 10 a.m., it has only minus 50 people. Right? And it has to do with this high variance. Now, there is a solution to this problem, which Sean Mine here, our collaborator, has come up with this sensor utility network estimator, which uses some model information to basically get rid of these drifts. But, finally, we'll have to use some sort of model information. But there is also a need for better occupancy sensors. So we looked at certain occupancy sensors and tested them out. CO2 sensors, of course, are one possibility. So this is an experiment we did in my lab. We came up with this new thing I'm very excited about. We call it cyber physical sensor. All right. So what it does is it's nothing but 2 lines of code that checks if somebody is active in a keyboard or a mouse. All right. So there are 5. This is my graduate student lab. There are 5 graduate students. And right now the software only works for Unix-based operating systems. And this guy decided to use a Windows PC, although I tried to convince him against it. But so right now I can install this software only in these 4 Mac computers. So we installed that. There's a video camera. We use the video camera to count number of people in automated fashion. And we will also install 2 CO2 sensors, one outside the window, one inside. So you look at differential CO2. That's really what you have to look at, outside CO2 minus inside CO2. Because CO2 varies, it could be because of variation in the outside. So that's by itself is not enough. So if you look at the output of all the sensors, so ground truth, this red line is the ground truth. How do you get the ground truth? There is no sensor for it. The sensor in this case is a graduate student who just looked through hours and hours of video feed. All right? And so this is the software sensor which looks at the video feed and does automated processing. And you can see this very large growth of error over time. CO2 sensors, it's all over the place. And it's not even actually number of occupants. I just looked at the parts per million count of coming out of a CO2 sensor, divide by some number. So it falls on the same y-axis. It's converting ppm measurements to number of occupants is also a very difficult problem. The one that worked the best is the CPS sensor, cyber physical sensor. So this is what we are trying to do in this PU hall, this other building. The conclusion is the problem is that it's a low occupancy office. You can probably do quite a bit with CO2 sensors if you have a room like this where occupancy is either 0 or let's say 50, right? Because then the CO2 level measurements will go above the noise level. In a small office, 2, 3, 1, 5 occupancy CO2 sensors won't give you anything. And of course, these flow rate-based sensors are not useful at all. So there is still need to some room to come up with better sensors. Right now, this sensor actually seems to work fine, and we are going to use that. The third component, so let me remind you of the components. Let me see. So we need occupancy prediction, temperature, humidity, indoor air quality. Well, temperature, humidity, you can model. Indoor air quality, we really cannot model. I mean, they're supposed to be just first order mass balance, but it depends on the indoor air quality, actually depends on the number of occupants and other things too. For example, how much upholstery is there in the room, because there are these volatile organic compounds that are given off by carpets, upholstery, the varnishes on furniture. That stuff is almost impossible to model. So you have to kind of do something without being able to predict it very accurately. And occupancy, we gave up on occupancy prediction for the moment. We say, okay, we can perhaps measure it. Predicting is going to be very hard. So we'll use some very simple first order models saying that occupancy in the next time instant is going to be same as the occupancy in the previous time instant. Hopefully it will lead to something. And there are environmental models which are basically weather, which I can get good predictions for. And if the environment is other zones, we can measure temperatures of the other zones, so that might be fine. And finally, we need to put all these components in a control and wrap a control loop around it. So the control algorithm is basically receding horizon control. What it does is, first of all, the occupancy forecast. We need prediction, right? And we don't really have good models for occupancy. So we use the very simple one. The next occupancy is equal to previous occupancy plus some noise. And you can do a linear prediction, which will be same thing as assuming that the next prediction is going to be the same as previous. And because we cannot model indoor air quality, or I mean, we can come up with some model, but very difficult to get good, accurate predictions, or virtually impossible. So what we have to do is build some amount of conservatism. We have to make sure that we supply enough air to maintain indoor air quality. And the other one is I'm not going to go through the details of it so much, but it just basically has 2 modes, occupied and unoccupied. And only difference is that in both cases, it just tries to compute the optimal value of some cost function, which is the total energy consumption in the next k minutes, which might be 30 minutes or 1 hour. Based on certain constraints. The difference between occupied and unoccupied mode is that constraints change. If you are currently in the unoccupied mode, you assume that I'm going to be in the unoccupied mode for the next half an hour, and I am allowed to vary the temperature within a wider range. And the indoor air and the supply air can go down to a particular level, but not below that. Whereas if I'm in the occupied mode, then I'm allowed to vary temperature only in a smaller range. All right? And the fact that this blue curve, which is the zone temperature, the fact that it goes to the lower level of the allowable limit is not an accident, although this was drawn by hand, is that if the AHU supplies air at 55 degrees, right? If you ask it to optimize energy consumption subject to this constraint, guess where it's going to go? It's going to go to the lower limit, right? So you have to be careful about that gap as well, because you can always cheat by making that gap really low and say, hey, I save energy. Oh, of course, because if you're letting the air temperature, room temperature drop quite a bit. And mass flow rates, at least some constant value plus something. And this constant value is to be there because one of the reasons is that we cannot really model indoor air quality dynamics very well. The other reason is that all of this occupancy prediction is based on occupancy measurements, and we have just seen how difficult even occupancy measurements are. So you will make errors in the occupancy measurement. So if you assume that the next 15-minute room is going to be unoccupied because I'm measuring right now it's unoccupied, well, what if the measurement is wrong, right? And so therefore, to build robustness into such errors, you have to put some conservatism into it. But even on doing all that, you can actually do much better than what you can do otherwise. So here is some simulation results. So the blue line is, this is the temperature of the zone. This is the model that is calibrated for that room 249 in Pew Hall in our campus. So this is what the conventional controller does, because in this case we decided to make the desired temperature right below 71 degree Fahrenheit. And then the black one is the temperature that is coming out of this controller. The red one is same sort of controller, except in this case we assume that we have perfect occupancy prediction. All right, I don't know where it comes from. Let's assume the best case scenario, somehow I have perfect occupancy prediction. And if I have that sort of long-term good prediction, what it will do is that it will let the temperature float to as close to the supply air temperature, 55, until about 20 minutes before it knows occupants are going to come in. At that time, it's going to ramp up just in time to meet the deadline when the occupants come in. All right. And now what happens with the black one, which is the controller I just described, because it doesn't have such good long-term prediction, when it is in the unoccupied mode, it does go down, but this is the design constraints are that, okay, you cannot go down below 69 because I don't know when it's going to suddenly switch to an occupied mode, and I have to bring it up quickly. So that's the only difference, and this is for this occupancy profile. Occupancy goes from 0 to 3 around mid-morning, and then lunchtime break, and then in the afternoon again occupied. Right. So here I'm showing total power, which is kind of a messy plot, but so let's not look at it too much. And the humidity ratio, again, it will be hard to interpret now, but you can trust me that it maintains humidity. All right. So what is the result that we get out of all this? For this room, energy consumption in megajoules, I forgot for what range of time this was. This is not power because I'm integrating over time. Conventional controller 1074. Occupancy, if you're doing this control, this receding horizon control, based only on currently measured occupancy and using that as a prediction for a short time, then I can bring it down to 552. So that's okay. So this 27% is wrong because there's another controller that we looked at. I removed this because it'll be too complicated to explain. So these are all incremental over the previous one. That's why this is, because this is like about 50%. So if you compare to that, it's about 50%. But it's 27% compared to the other one, which I'm not going to talk about. And if you have perfect occupancy prediction, then you can bring that energy consumption down to 355, which is 37% more compared to the previous one, which is with occupancy measurement only. But before you look at these numbers and become really happy, we have to remember that this is, first of all, it's a strong function of occupancy. These numbers are for that occupancy profile I showed. If the room is occupied 18 out of 24 hours, then the savings are only about 10%, which is understandable because the room is occupied all the time. You have to keep supplying air and maintain temperature, right? And the other is that it's also a strong function of all these design variables, the zone parameters, the RC values, the model, and the boundary conditions. What are the temperatures and I guess temperatures in the nearby zones? But the big thing that comes out of this is that just with occupancy measurement, I can still save quite a bit of energy. Right? So large savings are possible only with measurement, even if we cannot predict occupancy very well. Now there are other issues that have to be looked at, which is the robustness to this prediction errors, because all of this is based on model information. And of course, the robustness to occupancy measurement errors, which are inevitably going to be there. Some amount of robustness is built into the control algorithm, but we need to study it more. And the key issue in all of this is, although I keep talking about temperature, is that it's not really temperature control, but really air quality and ventilation. That's the key. As I said earlier, if you temperature is not maintained very well, you'll only be uncomfortable. But if your air quality is poor for long periods of time, then people will get sick, and it will lead to what is called the sick building syndrome. I mean, I actually tried this, not this control algorithm, it's too sophisticated for. I did manual control in my apartment. My earlier apartment was at ground floor. Although it's in Florida, it gets hot and humid in the summer. There are a lot of trees around it. So I thought, okay, maybe it won't get that hot in the summer. So what I would do is I turn the AC off. And of course, before I turn the AC on to bring it down to some tolerable temperature, I have to shut down all the windows, right? Otherwise, it will not be efficient. So after I shut the AC off, after all that, it very quickly becomes uncomfortable because there is no fresh air supply. So I have to go out and open the window, in which case it gets warm again, or I have to turn the AC on again. So that didn't work, so then I switched apartments. I actually was lucky enough to find this very nice apartment. Well, nice in the sense from this that it actually has cross ventilation, which is a very rare thing to find. So there's this big door that opens to a balcony, and then diagonally opposite to that, there's this window. So if I open the window, open the door, I get nice cross ventilation. So in 2010 summer, what I did was I did not run the AC for a single minute in the whole summer. And I kept the fan on, and it was still tolerable, only because there was fresh air. I mean, it was hot, but I grew up in a hot place. So and plus I was doing experiment in the interest of science. I can tolerate a little bit, right? So so I used to get all these letters from my utility. Your performance compared to your efficient neighbors. So I was like always number 1, 2, 3. Actually, I was never number 1. That always bugged me. I don't know why I never got to number 1. Let me see, how much time do I have? Not very much. So now we are trying to do all this in a real building. So this is the Pew Hall. And we quickly found out that we could not do this using the building management system or building automation system, because these things just don't work very well. Even to save data, I asked it to save data for 7 days, and then my students walk to this other building where data is supposed to be there, tries to download the file, 2 days of data are missing. I don't know why it happens, but this is not fault of this particular system. I have read in papers that all building management systems suffer from this sort of robustness issues. So one of my colleagues, Tim Middlecoop, he built his own backnet stack server, starting from scratch. It's kind of funny. You have to kind of log into this IP address of this modular equipment controllers, and you have to feed commands one line at a time. You have to telnet into this device. So just programming these things is also a big problem. But now we actually have this server running inside the building because of security issues. There is a Linux box without a keyboard, so that nobody can go in and try something with it. But he can control it. We can control that server through 2 other computers in the campus. Only 2 computers are allowed access to that. And they have to secure communication through VLAN. And all the data is being dumped into a Postgres database. So one of the things that we have to do right now is to build a state estimator, because otherwise there is no feedback in this receding horizon controller I showed you. And there are some issues there too, because these RC network models, the funny thing is that they frequently lead to unobservable systems. The nonlinear part actually helps you. It creates a time variation, but it only works for certain parameter values. So this is a big issue that we have to resolve pretty soon. And getting all the software to work, because we have to put occupancy sensors and they have to communicate over various interfaces. And there are like 7 different networks that you have to kind of make sure data flows through. So we are still working on that. Control of multiple zones. I'm going to skip this part. Right now we are doing some experiments, and it's not even clear we need to worry about this multi-zone case. So I'm going to skip this. One work I want to advertise is this work done by Prashant Mehta student Kundeng, who should be here. He's one of the organizers of this workshop. For doing this model reduction, because these buildings, if you look at multiple zones, these models quickly explode in complexity, these RC network models. But he came up with this very nice method of reducing the order while maintaining this physical intuition of the RC network models. So you get a very big RC network model, you reduce it applying this method, and you get another RC network model of much lower complexity. So it actually maintains the physical intuition. So that's very nice. Okay, I'm getting close to the end of my time, so I'm going to spend a little bit of time talking about this last part, which has to do with this all software and things like that, actually implementing these things. So ensuring persistency. What do I mean by that? Suppose I come up with this controller that I just showed you, and I implement this, and we do some experiments, and it all works fine. It saves 50% energy. The question is, oh, there it is. Kunde, I just advertised your work. You are not even there. All right. Okay. So the question is, how long do you think this is going to continue to deliver performance? And that's a problem, because even right now, buildings do not maintain a given level of performance. So people frequently do what is called retuning. Not everybody, but the building owners and operators who are serious about making sure that the building operates in an efficient manner, they frequently go through this retuning process. Engineers come in, they look at the data, they look at all the equipment, make sure nothing is stuck, because all these dampers that are supposed to control flows, mechanical components, right? They rust, they get jammed, and then nothing happens. Electronically, you'll get some signals, but you don't really know where the problem is. So they look at all this and they fix this. So the performance then gets a boost. But then it slowly creeps back down, right? And then until the next retuning. And the reason is, why does it lose performance over time? Well, various reasons. One is, of course, equipment failure, sensor failure, things like that. One of the other bigger reasons for this slow creep down of performance is operator overrides. So what happens is that somebody is uncomfortable, calls up the service department, and these building automation systems are actually, right now, they're very complicated systems. So even operators that are not well trained do not fully understand it. So they try to fix it, cannot seem to fix it. So what they do is they override whatever control algorithms are there, and so all that, even if you program this thing to give you the best possible performance within what is possible in the system, operator comes in, overrides it, all that is gone. And what's even worse is that they do global changes in response to local comfort complaints. So you complain that in my office is cold, they cannot fix what's happening in that office. So go back to the central computer, and then they change the whole setting of the whole building. So, and that is the reason why you see this room temperature being maintained around 72 throughout 24 hours. It's not supposed to be. There's a schedule. That's actually a Microsoft Word document, all right, that says how it's supposed to be maintained. And the schedule says, I'm going to show you right here. This is one part of the schedule. It says nighttime set point 84 and 62, meaning that I did not write down the nighttime, what it actually is nighttime according to them. But nighttime here is actually anytime between, I think, after 9 p.m. at night and 6 a.m. in the morning. It's supposed to be allowed to float anytime, any range between 62 degree Fahrenheit, 84 degree Fahrenheit. But it's not doing that. It's maintaining 70 or 73 throughout 24 hours. So forget about fancy receding horizon control. If you just make sure that the buildings operate as they are supposed to, you'll already save quite a bit of energy. So why is it not done? Well, of course, one problem is operator overrides because of poor training and all that. Other problem is that these building management systems are very complex, and it's very hard to understand what happens if you change one. If you change one thing here, what happens to the other thing somewhere else? And the real problem is this data deluge. So these things produce enormous amount of data. This is the software interface. Actually, somebody programs the building in it. You click on that room, and it will show you all the things, all the gory details of the what is called the variable air volume box. It will even show you a picture of the box if you don't know how it looks like. So, and it will show all the data, all the sensor measurements of that. And of course, you can plot all these things. There are interfaces for plotting, but it's an enormous amount of data. And who has time to look at all this? Nobody, because, well, that's actually a bigger thing, the economics of it, right? University of Florida, most of what I know comes from looking at these systems in my campus. University of Florida has hundreds of buildings, and all of those buildings, including maintaining HVAC system and the door locks, the whole range of operation, it's up to what is called the physical plants division. And physical plants division has 35 full-time employees. Hundreds of buildings, 35 full-time employees. And that number is not going to change anytime soon, not in a positive direction, because organizations and universities are not getting any richer, right? So things are only going to go in the other direction. So few people have to maintain and make sure all these things work. And right now they have a lot of data, but there is no way to actually use this data in an efficient manner. Another thing is, these operating schedules. Somebody comes up with a schedule, this is how it should be done, and this is a Microsoft Word document, vague set of instructions, and somebody has to convert all that into this 60s looking program. I think it's like Fortran code. I don't know. It's not Fortran. It's vendor specific. That's the other problem. All right. This is for a Siemens system. For a Siemens system, you have one programming language. If you go to Johnson Control, that will be another programming language. So what breaks between here and there, nobody knows. So this is supposed to be codified in this code, and it's supposed to lead to something good, but does not lead to what is supposed to happen. So one of the problems is this good software, basically. Right? Make sure that all this information does not have, there are so many points of failure now for information to break down. So if you can write good software which will, not Microsoft Word documents, right? So in a way that somebody can specify what is supposed to happen in one software framework, and that gets automatically translated to the code that a building automation system can understand. And then when the data actually finally becomes available, that has to be also analyzed in an automated fashion to the extent possible. You cannot ask an operator to look at all these plots and figure out, I mean, somebody looks at this plot, he will know, yes, something is wrong. But then that's a problem with the building, what is it called? Monitoring. So the building monitoring is a big thing now. And there are a lot of people who talk to me about building monitoring. So whoever wants to do this, at least in University of Florida, there are various people trying to do aspects of this. And when they learn about our project, they come talk to me and my colleague Tim Middlecoop. So I ask them, okay, you want to do building monitoring for what? So well, so that I can improve efficiency. Okay, but how? How is building monitoring going to lead to efficiency? There's a big gap between how actually monitoring is going to lead to efficiency, and that can only happen if we have good software and good information processing routines that can automatically sift through this tons and tons of data and tell you immediately what needs to change, or in fact, better still, do correction by itself. And the other problem is that right now, information flows from occupants or spaces to the building automation system through sensors and networks. And then that takes some control action, which has some effect on the occupants, but there is no information flow from the building automation system to the occupants. I think that's a tremendous opportunity there. Because if you let people know that, look, tomorrow it's going to be hot because I cannot buy as much power from my utilities, or if you have renewables, now renewables is a big thing, and I can only supply this much power, I am going to change the set points, and this is how it's going to be. People can take actions for that, and I think if you let information flow from what the building is doing and let it be known to the occupants, there is some opportunity for saving even more energy. Other problem is, of course, information longevity, because all these software vendors, they keep changing their version, right? So what happens, so what works today is not going to work tomorrow because one part of that whole flow breaks down. So the last question is, I'm supposed to talk about control and modeling issues. One of the biggest issues is fundamental limits. I mean, you can go on improving these things, but the question is, what is the fundamental limit on the efficiency of buildings? So that particular report said we should be able to improve to 55% over current baseline. Maybe we can improve up to 70%, I don't know, or maybe we cannot. Maybe we can only improve 20%. So this question of fundamental limits is important. Of course, we need all these components, sensors, models, algorithms. These first three I spent quite a bit of time talking. Software is, I did not spend as much time, but this I believe has got even more impact on the overall performance than even control algorithms and models. So finally, acknowledgement to everyone involved again, and National Science Foundation. And if you are interested in this and our current work, there is more information on my website. So you're welcome to visit that. Thank you for your attention.
So that's something. We have a few minutes for some questions.
So you're saying that if I try to control all the zones together, are you talking about control like the temperature control, or talking about the CO2 parts mostly? Yeah, okay, so Yeah, so that's going to be a little bit hard. There have been quite a few papers recently. I have actually reviewed a bunch of papers submitted to ACC on controlling like all the zones together. Most of the papers are... Oh, okay, okay, okay. One zone, but controlling all of that. So, yeah, so I mean, it can be done. Like our model already has temperature and humidity. I didn't put CO2 in there. It's possible, but the problem is how much do you trust your model, because the big part of CO2 dynamics comes from occupancy. It's the occupants that produce CO2. So if you can, the two things get linked, and if you have good prediction of occupancy, then that part of the model will work fine. But if not, then the prediction of that part of the model will be useless. So that's the problem. Yes. Right. Yes, there's definitely potential for that. If I understand you correctly, what you're saying is that if you have multiple zones, of course, what happens in that zone should affect what happens here, and you have basically everything you do in one, every zone basically affects every other zone. That's what you're saying, right? Oh yes, yeah, that's definitely true. So if you go to newer designs, then the opportunities just open up, and that's definitely something that should be looked at. I did not, because the problem I talked about, okay, which new system do you look at now? But definitely that's something that can be looked at. If you have multiple actuators, you can definitely do better. How much better, I don't know. And how to do it, of course, is another question. But I think I would agree with you on that. Yes, I think you can do better if you have multiple actuators. Yes. It is not much more advanced, just 2 lines of code. But you don't want to look at the screensaver, because screensaver depends on settings that the user has set, right? So if somebody says, don't turn the screensaver on for, I don't know, slide the bar all the way to the right. Some people do that, right, sometimes. So then you don't want to do that. But yeah, I mean, whatever works. There's a question from here, yes. Yeah, it's economics.
It's not a technology.
No. In fact, there is a problem there, in a sense that if you do not put right policies in place, all of this is not going to save any energy, because the economic benefits that you obtain by saving energy here, people are going to use that to consume some other source of energy, which is what happened in the automobile industry. I'm not sure if I understood that. Yeah, it's a detection estimation problem. The difficulty comes from lack of good models, because the highly stochastic process, this movement of occupants in and out of rooms. So how the occupancy varies in a room, it's a very difficult thing to predict, because it's a difficult thing to model. That's the difficulty. I don't know if is that what you were asking? Probably not.
Yeah, I'm saying, looking at this program as a search and tracking program. So
Okay, I mean, that can be done if you install a whole bunch of video sensors, for example, throughout the building, and you track occupants and correlate this occupant went out of view, but I see the same person in the other camera, and etc. You can do, but then that's a research problem. Yes, can be done, I guess, but there are privacy issues. So this $4,000 sensors we installed, the reason they are so expensive is that they do all this. It's a video-based, but thermal video-based sensor. It does all the processing on board and only shows you these circles moving. So you don't actually see the face of the person. Yes.
I don't know if you thought about this, but if you have a large office building with people come in having to like slide a card or something, right? Every card is this, I don't know, scan and you know where it's supposed to sit.
Right.
You can turn on.
Oh yes, yes. I think all sources of information should be leveraged. People's Microsoft calendar, Microsoft Office calendar, Google calendar, right? All of that information can be leveraged. How to do it? You have to build, you have to build good software to make sure that all this information flows properly. But yeah, it can be done and should be done. Actually, there's this question from here. Yes.
Yeah, actually, two questions. The first one is in terms of sensors. So, the traffic lights, there are very simple sensors that are able to detect numbers of vehicles that are queued up. So, one would think that there's something, if they can do it for a stochastic population of vehicles, then it shouldn't be that much different for populations of people. So that was one question. And the other question is that availability of renewable energy for wind is much more prevalent, much more available at night time. And so there's lots of talk about dumping the energy into chemical storage, batteries, but there's also an idea of dumping the energy into buildings and using the thermal storage capability within buildings. And in my naive view of that, we had talked about cooling the buildings down overnight. When you talk about the mechanism of control that is in place here at the moment, maybe it should be heating buildings up overnight. But anyway, how would you, moving beyond just the building to look at larger energy systems,
Right.
what's the mechanism for utilizing or storing renewable energy in buildings?
Yeah, I do believe there is tremendous potential for buildings to provide this service in the smart grid, because think about the chiller plants. In cooling down the individual buildings is one option, but these chiller plants, they produce chilled water, and then the chilled water is later used to condition the building later on. Nighttime, wind is available, produce chilled water at that time, and they already have storage. They may not have as much storage, so all you have to do is build a bigger storage tank. So, and that will be a perfect way to do this. You can do structure cooling as well for cool down the building at night. People already do that in certain places. They cool down the building at night because they know the next day at 2 p.m. electricity charges are going to skyrocket. Now, right now it's a bad idea. It's a good idea for them in the sense that it saves money, but does not save energy. You actually consume more energy that way. Save money because energy is cheaper at night. But with renewables, right, you are not producing more emissions by doing that at night. So that's a perfect way of doing it. I think buildings can be what we are looking for to make the smart grid more even out the demand in the smart grid. Now, in terms of your first question, well, let me take some other question. I'll come back to that because I'm not quite sure exactly how to do pressure pads too. Yes.
Europe has been using underfloor diffusers for a while. This country
I'm sorry. Europe has been using what?
underfloor diffusers.
Underfloor diffusers. Okay.
Yeah, this country, I know, has started to put them in their buildings. Do you have any experience with that? What do you think about it?
No, this is one thing that I decided not to look into because there are too many design variations. I have to focus at one thing. So yeah, I am not knowledgeable about. It's called radiant heating, I think. Not knowledgeable about that.
We have time for one more question. So part of my question was what was already asked, but I have two more small questions.
I don't think multiple questions. One question, please.
It's related. The first is that why do we really need very accurate occupancy models? Isn't it? It's not exactly binary as case of lighting,
Right.
but you can always have a plus minus 5 error in the number of occupants, and the marginal change in the heat that the occupants release or the humidity that they affect, it won't be that much. Right?
Did you ask me this question in last year in the Georgia Tech symposium?
No.
No, somebody asked me a question like that, and you are right. We don't need very high. Well, right answer is I really do not know exactly how much accuracy is needed. So what we showed, what we found out is that we don't really need that high accuracy in terms of prediction. Right? Just using measurement is enough. Now I think the accuracy it's a nonlinear function in the sense that as the true occupancy comes closer to 0, your need for accuracy increases.
Yes.
Right? On the other side, it's probably not as much.
We need boundary values, that if it's occupied or not.
Yeah, sometimes that's all you only matter, right? But
Follow-up question is that I agree that the main culprit for energy consumption in buildings is HVAC, but specifically if you just look at VFVs and reheat coils, how much of percentage do they contribute to what total HVAC consumes? Because another factor is another consumption, the equipment that uses a lot of energy is the pumps which circulate air. They use a lot of energy because they are motors and they have to run continuously. Whereas locally heat only is done
Right.
a couple of minutes, 5 times a minute or once every half an hour or something like that.
well, see, in terms of the fans that circulate air, that's what I read too, that they consume a lot of energy. But I'm not quite sure because we looked at energy consumption from the fans in this building because we can read what is called the VFDs, variable frequency drives. And over a period of a month, what we saw is that fans actually are consuming only about 10% of the total energy consumption. So it was actually much lower than the numbers that I have been reading. I don't quite yet know why that is happening. Maybe the reheating, in here the plots I showed you, reheating consumes about 30 or 40% of the energy, right? So maybe the reheating is so much higher that it's actually pressing down the fan energy. But all of these components are important. You know, there's first the cooling and the fans, and then the reheating at the end.
Let's bring the question on offline. Thanks again.
Thank you.
Actually, the management committee has prepared a present.
Oh, okay.
Please give to you.
Thank you.
This ends on Zoom session at 2:30, and if you have closer sessions at MEL, please go there at